Good afternoon to all of you. I am Shefali Agrawal from the Indian Institute of Remote Sensing. Today's session, what we will discuss is an overview on hyperspectral remote sensing technology. I'll just try to go through what is hyperspectral remote sensing, the significance of this technology, what are the different sensors or the satellite sensors or the instruments available for providing such kind of data, and the application potential of this, and what is a very brief into the overview of the processing aspects of hyperspectral and how it is different from the multispectral data sets. So first of all, if you consider that if you look at it, that is from the previous lectures on remote sensing, the physical properties which help in identification and quantification of features, which are primarily the three properties. This is the reflectance characteristics, transmittivity, and the emissivity. So any interaction, if you look at between the electromagnetic radiation and the Earth's surface feature, you get three interaction mechanisms, which is the energy is scattered on interacting, and some part of it is reflected. The other is it gets transmitted and absorbed. This absorbed energy is later on re-emitted. So these are the three properties which enable us to differentiate different type of land cover features onto the Earth on a satellite data set. Now, from this itself, if we talk about what is a spectrum, if we say electromagnetic spectrum or electromagnetic signatures, it is the variation of quantity of energy as a function of its wavelength. That is what we call it as a spectral signature in the entire spectrum. And what is varying? The quantity of energy can either be reflected, what we saw, emitted, or transmitted. Now this is what is enabling us to we measure these quantities, and these quantities, what is measured, we analyze, and it enables us to differentiate between different land cover features. Now the question arises, like, what should be the sampling interval in the spectrum? We can have a broadband, where my sampling interval is very broad enough. For example, if I take one more example before this, where we have a panchromatic data, where my sampling interval is from 0.4 to 0.7 micrometers, that is, it's approximately 300 nanometer of my bandwidth, then I get a certain response from the object when it interacts with different parts of the electromagnetic radiation. Now the same spectra can be observed in a slightly narrower bandwidth of 100 nanometers, where I have the bandwidth of, say here, 0.45 to 0.52, 0.52 to 0.60. So I've broken the same spectra into narrow sampling rates, which is around in the range of 80 to 100 nanometers. So the number of observation increases. So here on the first broadband, this is the entire spectrum is from the visible spectra, and this is from the infrared and the long wave infrared. So the two major observations in the visible and the infrared and the long wave infrared. Similarly, if I break it down, increase my sampling interval in terms of the wavelengths, we have the multispectral remote sensing, which you already are aware from the previous lectures. Now, in the same band, if I reduce my sampling interval and make my observation interval narrower to 20 or less than 20 or in the order of 30 nanometers, then we have large number of bands. So these kind of data sets, we have bands of the order of 100 to 200 bands. So this kind of data is known as hyperspectral remote sensing data. We have certain advantages with this data. What are those? We'll just cover in subsequently. Then instead of, if you make my sampling interval, my bandwidth difference between the two sampling bands, as 5 to 10 nanometers, then I have much more bands available for me to analyze. We go up to the order of thousands of bands where we get what we call as ultraspectral remote sensing. What you can say is an hyperspectral remote sensing data. It's a branch of imaging spectroscopy which refers to imaging of the scene over a large number of discrete contiguous bands that are visible to the infrared region up to 2.5 micrometer, such that the complete spectrum can be obtained about the feature. So at any point of time, you can have a complete spectra because of the narrow sampling rate. So here, hyperspectral remote sensing is basically a combination of imaging and spectroscopy into a single system. It's an imaging device and a spectroscopy, because if you remember from the spectroscopy means studying of the interaction mechanism or the energy in a very, very narrow sampling interval rate and across the entire spectrum. So what we get, we can cooperate, we get larger data sets and requires, since we have large amount of data, definitely we require new processing methods to process these kinds of data. So it's a science of acquiring digital imagery of the Earth material in narrow contiguous spectral bands. So here you should note down there are two things: narrowness of the sampling interval and contiguity of the spectral band. That means it should be contiguous in nature. It should not be discrete and gaps in between. So here you look at the same concept is represented here graphically. We have three kinds of information in remote sensing. We have spatial information, we have intensity information. Spatial is the dimension, the size of your data sets, that is the spatial resolution what we talk about, 1 meter, 10 meter, 5 meter, 20 meters. Then the intensity information relates to your energy being reflected, that is your DN values, and the spectral information, which is your spectral resolution, relates to your the spectral dimensions. Now here we have different instruments for measuring these three quantities. Spatial information, it can be measured by imagers, it can be cameras or multispectral scanners. So these are the devices which measure spatial information. Radiometers, they measure the intensity information in predefined interval wavelengths. Then what we have is the spectrometers. Now spectrometers give us continuous observations across the entire spectrum. The spectral information comes from the spectrometer. A combination of all the three technologies would give me imaging spectroradiometers. A combination of imagers and spectral information, that is spectrometers, what emerges out is an imaging spectrometer, which is used for ground either on ground or on space base, but they give you a continuous observations. Then a combination of imagers and radiometers. These are imaging radiometers, which are your multispectral cameras. Then a combination of, if I have a spectrometry property, that means I have very narrow fine intervals, and at every interval I'm measuring the intensity information. We have spectroradiometers which are used for as a ground instrument for validation. So here at any point of time, if you click at an object or a field of view, for that location you get a complete range of values, the reflected energy at every narrow interval of the wavelength. So it's a triangular concept that all three together, it combines together to get imaging spectroradiometers. So it's a combination of imagers, spectrometers, and radiometers. Now, what is the basic principle? Why we use hyperspectral remote sensing? As I mentioned earlier, that in remote sensing, what are we looking? We are trying to identify different land use, land cover type, different features on the Earth's surface. That is the main purpose. And to identify different minerals, different composition. As much better we can classify the features on the Earth's surface. So each of the Earth's surface features, when it interacts with the energy, it is either reflected, absorbed, or transmitted. But then the location and shape, what happens is, if you look at any spectra, in each interaction or in each spectral curve, the interaction mechanism, either for vegetation or for soil or for water, you will have some places the energy is reflected, the other the energy gets absorbed. Then there is this continues throughout the, and depending on the type or the composition of the material, the absorption features occurs, and there is a high reflectance at some point of time. So various materials absorb sunlight over specific wavelength intervals, which is very, very characteristic of that particular object on ground. And these are known as, these absorption zones are called as absorption features in the reflectance spectra. And the location and the shape of these unique spectra, these unique absorption features are very, very important, and they provide information onto the chemical composition of the material. Reflectance spectra enables us to discriminate between the two types, but these absorption features which are available, they are very unique to that object. So the moment the composition or the material characteristic changes, the absorption location and the shape changes. So in a way, they enable us to identify the exact type of the material and its chemical composition also. So due to this, we are in case of multispectral, you're able to perform up to a certain level of identification. Then for further enhancing it to exactly target what it is on ground, what it is composed of, we need data sets where we can have large number of observations. And since these observations at some point of time is so narrow in nature, when we take observations at a broad sampling or a sampling rate in terms of the spectra, the electronic spectrum, then we miss out with these absorption zones. So to get or to capture these narrow absorption zones, we require a finer sampling interval in the wavelength region. So that is why the hyperspectral remote sensing has an importance in identification of features, and it enables us in doing so. So in tapes of hyperspectral remote sensing, you have the image where it's a three-dimensional image. X and Y corresponds to its spatial pixels, and the Z dimension is the number of spectral bands. So here you have hundreds plus bands which is available. At any point of time, if you look, the pixel value is plotted, you get a complete spectra which matches to the ground spectra measured using a ground radiometer. So this is another example. So if you look, we have the spectra for the soil, water, and vegetation. So if you look, they match exactly to what is being referred into a textbook. So the spectra closely resembles to very closely resembles to the spectra which you mention, which you see in the reference for vegetation, water, and soil. And these finer observations enable us to identify the exact composition as well as material type. Here, if I can say, we can compare the multispectral versus hyperspectral. The multispectral, you have separated spectral bands. There is no contiguity. Whereas in hyperspectral, they are contiguous in nature. There is no spectral gap. And this is the prime requirement for a data to qualify as hyperspectral. We may have a very fine sampling rate, but there is no contiguity in the data. There is separated bands. There are gaps in my observations. Then the data does not qualify to be a hyperspectral data set. Then broadband remote sensing, they have a broad, as we saw previously saw, they have a wider nano bandwidth, that is of the order of 100 nanometers, whereas hyperspectral remote sensing, they have a narrow bandwidth of 10 to 20 nanometers. When the multispectral, they have a they represent spectral signature in a coarse manner because there are gaps in between, and the observation period or the interval is very broad in nature, whereas the hyperspectral, they completely represent the spectral signature. The signature matches to the reference spectra. This is one example of where you see how the data spectrum changes for a feature from a multispectral to a hyperspectral data set. So we have, in case of Landsat, if you look at this graph, the Landsat observations, it has 6 bands, and the 7th band is in the thermal infrared. So this is a spectra from 0 to 2.5 micrometers. In case you have a sampling interval at very broad distances, there are gaps in between here, and finally you get the data in a very coarser resolution in terms of spectral resolution. The MODIS, which has 20 bands in this case, for the observations, there also you will find the sampling intervals are very, very far away. So still it is better than the Landsat. But with the AVIRS data, which is having around 224 bands with a sampling in spectral bandwidth of 5 to 10 nanometers, then if you look at it, it shows a complete profile. The profile matches to your hyperspectral lab profile. So this is the difference, and when we get such a profile, we are able to clearly differentiate between different types of species if it is a vegetation, different types of minerals if it is in terms of geology, or for various applications. So feature identification becomes much more easier. So the molecular makeup of the material results in patterns of reflectance and absorption, as I can summarize, across the wavelengths that often uniquely identify a material. Therefore, by looking at a pixel spectrum from a spectral image, we can identify the materials existing inside the pixel, whereas multispectral sensors measure multiple wide separated wavebands, and hyperspectral sensors measure multiple narrow and contiguous wavebands. So that is the strength of the hyperspectral remote sensing data sets. The word of caution that says hyperspectral sensors, they can measure hundreds of wavelengths, and most multispectral sensors measures only few wavelengths. But it is not the number which is the case which qualifies it to be a hyperspectral, but the contiguous narrowness as well as the contiguous nature of the measurements qualify for any data to be called as hyperspectral. You can take an example that if I have a sensor that measured only 20 bands, could be considered a hyperspectral if the bands are contiguous and the bandwidth is of the order of 10 to 20 nanometers. If I have a sensor which measured 20 wavelength bands that were 100 nanometer wide or separated by gaps in between, it's discrete in nature, then the sensor would be considered as multispectral. So it's not the number which quantifies it to be a hyperspectral, but the contiguous nature of it also matters. This is another example of the spectral reflectance of 3 features: vegetation, soil, and a mineral. Now this is with Landsat. You can see the nature of the profile. How is it? We have only very few observations. It's a straight observations in between. The gaps are there. The same observation, when again taken with AVIRS dataset, you can observe it gives you a complete spectral profile which exactly matches with your textbook or the ground profile. So this is for vegetation. It matches exactly the spectra which you have read previously in the lectures to be that as a vegetation spectra. This is for the soil, and this is for the mineral talc. This has an sampling interval of 10 nanometers. Now, why do we get the spectra? So here if you see, differences in absorption and scattering for different wavelengths results in spectra. And why do we get, in fact, these absorptions, what we are there? These absorptions which we get are caused by the molecular absorptions, and the molecular absorptions are resulted due to the various processes like electronic, vibrational, and rotational process. Now this, if you look as an example here, this is a feature between the two types of rocks. Now alunite and quartz, if you look at it, the absorption at one point is at 2.1 nanometers and the other is at 2.2 nanometers. So hardly there is a difference of 10 nanometers. If I make a broadband observations from 2 to 3, 2 micrometers to 3 micrometers, that is 100 nanometer bandwidth, these absorptions between the two would be lost and they would not give much of a variation. The value here will not reflect the two as a different. They may have a similar value. But when I make a very fine observations, then I have an observations from 2 to 2.1 and then 2.1 to 2.2. So I'm able to capture these absorption, and which will enable me to differentiate one spectra with respect to the other, and thereby enabling me to differentiate between the two minerals or the rock types. Further, a better example of this which shows that these two are able to differentiate between the two. Now the properties of the land cover which is able to differentiate is the chemical, physical and the mechanical. What we measure from satellite is the reflective and the emissive properties. So from the reflective properties, and when we have a larger sampling rate, we can assess the chemical composition. To some extent, no, because these are the three properties of an object which vary from one object to other, is the chemical, physical and the mechanical properties. Directly what we assess from remote sensing or what we measure is the reflective and the emissivity. But when we have a large sampling rate like hyperspectral, then using the reflective properties in a very narrow sampling rate, we can, using that, try to estimate the chemical composition of the objects on the ground. So the absorption processes which are there, as I said, why do these absorption occur? So the interaction of the electromagnetic radiation with atoms and molecules creates absorption features in the spectra. Now these absorption features are basically fundamental features are fundamentals, overtones and combinations which occur due to three processes: vibrational, rotational and electronic processes. Within electronic processes we have another category which is the charge transfer process. Now the electronic process, these occur in the visible region, whereas the vibrational processes and the vibrational processes occur in the visible and the near infrared regions. Because each of the molecules, because it's a process, the absorptions are caused by the molecules, and molecules have three types of energy levels, which is electronic, vibrational and rotations. And transition between the electronics level basically occurs mainly in the ultraviolet radiations or the near visible radiations. Transitions in the vibrational energy levels, they occur in the visible and the near infrared. And the rotational processes causes absorption in the far infrared region of the electromagnetic spectrum. And the four important infrared absorbers of the molecules are the water molecules, carbon dioxide, ozone, and the methane. Now the charge transfer process is let's talk about the electronic process. Electronic process is isolated atoms and ions have discrete energy states, and absorption of photons of a specific wavelength causes a change from one energy state to a high energy state. An emission of a photon results in a change of energy state to a lower one. So basically this causes the absorption of the energy, and when the electrons move from the lower to a higher energy state. And the charge for transfer absorption, they are caused when the electron is transferred to another ion or liquid, ion or ligand, due to the absorption of a photon. And they cause large absorptions and in the visible region of the ultraviolet spectrum. And the absorption regions are quite large, and it occurs in from transitions from Fe3 to Fe2, and these transitions are so large, the absorptions are so large that they can be easily detected even in the visible or multispectral remote sensing, and they are primarily, as I said, in the visible region of the electromagnetic spectra. So here if you look, these are the absorptions for the iron, different compositions of iron here, and these absorptions are very broad in nature, and they can be easily captured using the multispectral sensors. And there is an overlap among the observation caused by different atoms, so they may be sometimes confusing, but they are very, very broad in nature, so it can be easily detected with the multispectral source. And electronic transition processes, basically, which is a crystal field effect. This is due to the crystal field effect, is this absorption of photons of a specific wavelength when it moves from a lower energy state to a high energy. And these absorptions are narrower than the charge transfer processes. And the wavelengths of the absorptions are controlled not only by the type of atom, but also the position and variety of its neighbors. And it occurs in chromium, cobalt, iron, copper, any of these metals which are there. It causes the absorption is there, and the absorption bandwidth is very, very small in dimension. And this feature is specially used in geological feature identification, since the subtle variation in the position of the band center are very important. It is necessary to have many narrowly spaced bands to take full advantage of these features. Next is the vibrational processes. Now the vibrational process is a typical here. I mean, in this case, these are due to the bonds in the which occurs in the liquid, the vibration of bonds in the liquids, because molecules are not static; they are in motion. So the vibration of bonds which occur in the liquids, solid or gases, causes this energy absorption. So vibration causes a variation in the energy, which is resulting in the absorption of the energy in the entire spectra. So the vibration form, therefore, a fundamental basis for spectroscopy, or very significant in the interaction mechanism between electromagnetic radiation and the object. And these have low energy, they occur in a higher wavelength, and the absorption again due to the vibrational processes is very, very narrow in nature, of the order of 10 to 20 nanometers, and these are the prime molecules which are causing the vibrational processes. They're the hydroxyl ions, carbon dioxide, the oxygen molecules. So basically the bonds in a molecule vibrate, and the frequency is dependent on the type of band and the atom masses. So certain materials have important vibrational absorption bands, like water, as I said, water molecule, hydroxyl, carbonates, phosphates, borates, so arsenates, silicates. So all of them, there is an absorption of energy due to the vibrational processes which occurs in it. So like for example, a water molecule has n equal to 3, that is there are 3n minus 6, that is equal to 3 fundamental vibrations, and due to which there is a shift in the frequency and the absorption of features occurs. So it is this kind of vibrational processes are very, very important in geological feature identification or mineral identification. So what we can say, this is a part of these processes is part of a spectroscopy or spectrometry. So spectrometry is what? It measures the absorption of wavelengths and absorption. What we do is we find the wavelength at which absorption occurs and the absorption depth, and this is used to estimate or to find the chemical composition and finally the type of material on the Earth's surface. We identify the mineral or the feature on the Earth's surface. So this is what it says. So the here usually occurs in a larger wavelength region of a very small order, and these are the molecules which causes the vibrational motion. The bonds between them causes the vibrational processes. So many of the absorptions seen, if you saw the previously, we had, due to the charge transfer, they were very broader in nature. They occurred in the visible processes, but the electronic process as well as the vibrational processes, most of the absorption due to these processes were seen in from 0.4 to 2.5 micrometer region, which actually originate at longer wavelengths, and most of these observations can be detected with hyperspectral sensors because the order of these absorptions were in the order from 10 to 20 nanometers. So these are few examples of different forms of absorption spectra. So here, there are absorptions at different points in the spectra. If you zoom up the small area, you can see the absorptions are at different wavelengths, and some of these absorptions are significant. If we are able to measure this absorption and the width of this absorption, compare it with the ground spectra, the width and the depth of this absorption, if we compare with the spectra collected using a ground instrument, if they exactly match together, then we can directly identify or infer and say this is this mineral or material on ground. So this is using the charge transfer, which is very broad in nature. This is for vegetation. There are two types of vegetation feature, pine and fir. And if you look, the absorption point is different for both the features. So this enables us, when we measure in the narrow wavelength, we can differentiate between pine and fir. If you are broadband observations, then these two would mix up together, and differentiation between pine and fir would be difficult. So from here we can then summarize as to the wavelength region and the kind of the minerals or the composition which enable us, which is playing a significant role for identification of those features. For example, in the wavelength region from 0.4 to 1.5, we have iron-bearing minerals, carbonates, and sulfates. So features having iron-bearing minerals, carbonates, and sulfates. Iron-bearing in the sense we saw that was due to the charge transfer. We had the absorption when the charge is transferred from one form of iron to the other, one state to one ion to another, Fe3 to Fe2, or similarly in other forms. Then we have the charge transfer, which is a broad band, but still it is useful for identifying the different type of the concentration of iron present in the mineral, and then that leads to the identification of the object on ground. Then we have the carbonates. Also similarly, they have carbonates causes narrow absorptions, but this region of wavelength, that means the near infrared region, are useful for carbonates and sulfates rather than the visible. Iron is dominant in the visible as well as in the infrared region. Then in the middle infrared and the shortwave infrared region, we can use to identify the objects with carbonates, the hydroxyl groups of carbonates, clay, etc. For vegetation features, in the visible region, primarily it is the chlorophyll, A and B pigments. In the near infrared region, it is a plant water content and cellulose. Then we have protein, starch, lignin, starch, protein, nitrogen, and cellulose. For snow and ice studies, the wavelength which is primarily important is the 0.4 to 0.8 micrometers for snow grain size, snow depth, and contaminants present in the snow. From 0.8 to 1.4, it's a snow grain size, liquid water content, and so on. Then the requirement of, that was the, in broader terms, the different wavelength which is suitable for identification of the different types of features. Then the requirement of the spectral resolution, or what we say sampling interval, required for different type of features. So for soils and geological investigation, mostly the near and the shortwave infrared is of prime importance, with a spatial resolution of 10 nanometers. This is to be nanometer resolution is necessary. And vegetation, we can have a range from the visible to the infrared with an optimum resolution again of 10 to 20 nanometers, and in some cases 5 to 10 nanometers. So in the visible region from 445 nanometers to 670, a 10 to nano bandwidth would be optimum enough for vegetation, water, and iron minerals. In the red and region, red to near infrared, it is 5 to 10 nanometers for vegetation, because this region is used for the red edge detection, which enables us to know the health of the plants or health of the vegetation. Then from 745 nanometers to 765 nanometers, an approximate 5 to 10 nanometer bandwidth for the applications of vegetation, atmospheric corrections is required. Then atmospheric studies, in fact. Then 780 to nanometers, around 5 to 10 nanometer bandwidth in this region for vegetation and again iron minerals. And 880 to 1035, 5 to 10 nanometers for again vegetation and iron minerals. For soils and rocks, for soil moisture study, a coarse spectral resolution would help in, that is of the order of 50 nanometers, and weak absorption bands of carbonates and dolomite and calcite for minerals, geological minerals. In the middle infrared and shortwave infrared, it's 10 nanometers. So as you can observe, in general, for all the applications, the order is varying from 5 to 20 nanometers. So most of the sensors which have been designed is of having an optimum bandwidth of 10 nanometers, which will help in identification of features in all the applications ranging from vegetation, soil, geology, and for atmospheric studies. atmospheric studies, node studies. So in fact, it covers the entire application areas if we have an optimum bandwidth of 10 nanometers, because the absorption zone which is there, it ranges primarily from 5 to 20 nanometers. So if we have 10 nanometers, we mostly cover all the applications. So if I can summarize, multispectral instruments can discriminate, hyperspectral instrument can identify materials on ground, on the images, using remote sensing images. The only advantage which I can say of multispectral over hyperspectral is the availability of data. So we don't have large number of hyperspectral sensors to take advantage of and use those data for processing, whereas the large number of multispectral sensors are available, accessible for use and application into different areas. And most of these hyperspectral sensors are for different countries. They have their own airborne hyperspectral sensors which they use for different research applications. And another limitations of hyperspectral sensor is they're since we have a very narrow bandwidth, they have large amount of noise. They're very sensitive to noise as compared to a multispectral scanner. It is very difficult to interpret the spectral signatures of impure pixels. If you have a mixed pixel problem, which you might be knowing it from the previous classes, mixed pixel is where in a single pixel you have a combination of different land use, land cover feature on the Earth. So in case of hyperspectral, since we have a large dimension of data, the spectra which you get is neither matching to any of the textbook because it is a combination of spectra from different features. So in this case, identification of that spectra is difficult. We have to go for another technique called unmixing approaches to find the constituent land cover features present within that pixel and then correlate it to its presence or existence and non-existence with respect to that particular class. And we need to calibrate hyperspectral data sets, because we want to compare this with the ground reference, and if we need to compare it to the ground reference, we need to correct the atmospheric disturbances or effects present in the data. So the atmospheric correction is primarily very important in case of hyperspectral data processing. The classification approaches also are different in comparison to multispectral because of the large dimension of the data. We have large correlation between the data sets, and some of the algorithms have their limitations. They work well with the small data sets because of the high dependency on the ground truth and your signatures which you collect, your training data sets. And since here the dimension is increasing, you cannot have this increasing number of training samples. So due to this constraint, we have different kinds of classification algorithms which are used with hyperspectral data sets. So the processing slightly differs from your multispectral to your hyperspectral remote sensing data. This is an example of a mixed pixel where within the same pixel, one big pixel, you have different land use, land cover classes and the presence of small or sub-pixel targets, and these transition from one land cover to class, and what happens is combinedly the spectra would be much different from the pure pixel. So that enables us to differentiate, difficult for us to differentiate the particular or identify the particular land cover present there. So another the limitation of hyperspectral is data volume and redundancy. So because of the large data volume and there is a correlation, large number of bands, not all the data is needed to characterize the pixel properties. Some overlap of information is there, and correlation is also available. So it's a redundancy of information is also there with hyperspectral. But besides these, once we correct for it using the processing methods, this data is very, very significant and is very useful, has a large amount of advantage in its processing. So in many applications, specifically in geology, vegetation, it plays a very, very crucial role. Now, the image before I proceed, can we have a break in between, and you can ask questions till now before I move to the second part where we talk about the acquisition modes, the applications, and the processing aspects of hyperspectral data. There's a slight change. We'll continue with the lecture and come back for the question and answer after the lecture is over. Now, the satellite image acquisition, as you all are aware, we have three modes of acquisition: whisk broom, push broom, and the aerial acquisition or steering, where we click frame by frame acquisition technology. So in hyperspectral also we have collection mechanism satellites or airborne sensors operating with whisk broom as well as push broom methods. So the working principle is nearly similar to your multispectral. Here the difference being that the detectors, instead of very discrete detectors, we have a grating instrument or a prism which splits the light into the energy which is being reflected. The sun's energy gets separated into different regions of the electromagnetic spectrum. It breaks it into the individual spectra, and then for each of them there is an array of detectors. So these array of detectors measures the energy in different narrow wavelength regions. So each of these sensors are sensitive to a particular narrow wavelength of the spectra. So the electromagnetic separated into distinct angles. The spectrum of a single ground pixel will be dispersed and focused at a different locations of one dimensions of the detector array. So the main important element here in the entire process is the grating instrument or the dispersing instrument, which separates the light into these finer nano interval of energy. So the number of sensors are available. Primarily they are more in airborne and spaceborne. The airborne sensors, we have the Canadian technology, compact airborne spectral imager, the American airborne visible infrared imaging spectrometer, HIDIS, the digital airborne imaging spectrometer. Hyperion, we have spaceborne, we have Hyperion, CRIS, MERIS, and few ground-based spectroradiometers are there for making ground-based observations. This is an example of a ground-based spectrometer. The spectral cover, we have, there are many, but I'm just mentioning two of them here: field spec and PSM 3500, which has a spectral range from 350 to 2500 nanometer. With a spectral resolution, it can go of the order of 3 nanometers in the up till the visible region of 700, and at the 10 nanometers up till 2100 nanometers or 1400, depending on what type of resolution is being purchased by the user. So, and there's a scanning time of 100 milliseconds, and then it uses the silicon photodiode detector, and it is used for a wide range of applications we'll talk about. So these are some ground instruments which can be used in the laboratory or on field to collect the spectra and compare the spectra with the image collected spectra for identification of features. Now, these are some of the list of the airborne hyperspectral sensors which are available. We have airborne imaging spectrometer, which is developed by JPL in 1983. In fact, the entire hyperspectral remote sensing was initiated with geological applications in the US by the JPL for identification of different gold and diamond mines in the United Nations. So the initiation was done for geological applications and expanded to vegetation and other areas, which has a wavelength range, which measures in the wavelength range from 0.8 to 2.5 micrometers with a bandwidth of 10 nanometers approximately, with 128 bands in it. Then we have a Florence line imager program, then by Canada in 84 with 0.4 to again, this has in the visible and the near infrared region with a bandwidth of 2.6 nanometers, which use the push broom technology and the grating instrument. It uses the push broom and the grating instrument. Then we have geophysical and environment research imaging spectrometers from the GER Corporation in United States. It has measures in the wavelength region from 0.4 to 2.5 micrometers with a variable bandwidth, and total number of 63 bands were there. It uses the whisk broom and the grating instrument. Airborne, the more commonly one, which the data of this is also available, even if you buy the NV software, the data, free sample data available for you to experiment. This is the airborne visible imaging infrared spectrometer in the wavelength range from 0.38 to 2.5 micrometers with a bandwidth of 10 nanometers and 224 bands, which also uses the whisk broom technology of acquisition and grating instrument for splitting the light into different constituents. The instrument which I also mentioned was the compact airborne spectroradiometer, spectrographic imager, which operates in the wavelength from 0.4 to 1.0 micrometers with a bandwidth of 2.9 nanometers with 288 bands, and the field of view is around 35 degrees, and it uses a push broom technology and the grating instruments from the European agency. This is an example of the airborne visual infrared imaging spectrometer data sets. This is used on and it can have a spatial resolution which is variable depending on the flight height. You can have a variable spatial resolution, and it has a sampling interval, or the radiometric resolution was 16 bits. Then another airborne sensor is the HiMap hyperspectral mapper, which offers in general 100 to 200 bands because it has a variable bandwidth which can be adjusted as per the requirement, and the spatial resolution also can be variable depending on the height of the aircraft. This is the instrument, that is the compact airborne spectrographic imager, which again is an airborne sensor, which what we saw with 288 bands, and the variable spatial resolution from 1 to 10 meters depending on the altitude by the Europe from the Calgary. The other sensors are HIDIS, developed by the US Navy, with 210 channels, spectral resolution of 10 nanometers, operating from around 413 to 2.5 around 0.4 to 2.5 micrometers, and the spatial dimension was 320 pixels, and the resolution was varying from 1 to 10, again with the flying height. Then the European Digital Airborne Imaging Spectrometer with 72 channels, 3 spectral channels, ranging from 400 to 1200 nanometers, and in that region it offered 15 to 30 nanometer bandwidth. In the wavelength region from 1500 to 1800 it offered 45 nanometers, and from 2000 to 2500 it is a 20 nanometer bandwidth. And the gaps in between which you are seeing are not gaps in the data, but basically they are atmospheric absorption bands, so no data is available. That's the reason they have not designed any detectors in these areas. Then the airborne sensors. The airborne sensors, the first of the airborne sensor which was initiated was Hyperion on board the Earth observation mission by the United States, along with the Landsat. So the Hyperion, the ground resolution or the spatial resolution is very similar to your Landsat data, that is 30 meters. The SWAT is very less, 7.65 kilometers, and the operating region of wavelength is 0.35, approximately 0.4 to 2.5 micrometers, with the bandwidth of 10 nanometers, and it was launched in 2000. Then we have FT hyperspectral imager, Mighty Sat-2, which is again by the US, with a spatial resolution of 58 to 29 meters, variable in the region swath between 7.5 to 30 kilometers, and the bandwidth varying from 2 to 20 nanometers. The other airborne sensor is CRIS, Compact High Resolution Imaging Sensor, which is launched by the European Space Agency in 2001 on board the Proba satellite. Then India also launched an hyperspectral sensor on board the Indian Mini Satellite 1 in 2008 called the Hyperspectral Imager. China also has launched one hyperspectral imager satellite called Hi-1A. Then the US in 2009 also launched another satellite, Hyperspectral Imager for Coastal Oceans, called on board the ISS satellite, and with a very coarse resolution, because in oceans we don't need a very high spatial resolution, but the spectral resolution is of the order of 10 nanometers in the spectral region from 0.38 to 1 micrometers. So from all of these, the Hyperion data now is freely available on the website, so one can download, you can browse for your area and download this data and use it for processing. So this is an example of Hyperion sensor. As we saw, the swath is very less, 7.5 kilometers, and it is 100 kilometers in the vertical dimensions. This is an example of the CRIS sensor on board the Proba satellite with 18 by 18 kilometer images with 18 meter resolution and 200 spectral bands. The Indian Mini Satellite sensor, it had 64 bands with a spatial resolution of 500 meters, and the spectral range from 0.4 to 0.95. In fact, this was an experiment, and after this we had the similar sensor but with a better spatial resolution, placed on board Chandrayaan-1, which along with the M-Cube data of the US helped for identification of water on Moon. So Chandrayaan-1 High-C, which had 64 contiguous bands in the visible and the near infrared, and the spectral range is from 0.4 to 0.95 micrometer region, with the improved spatial resolution from 500 meters to 80 meters, and the spectral bandwidth was 15 nanometers, and the swath coverage of 20 kilometers. Then there is another satellite for the atmospheric applications, that is atmospheric infrared sounder, which has a swath of 1.650 kilometers. It has an infrared spectral coverage with 2,378 channels, and primarily used for measuring the atmospheric properties and parameters. This also, some of the data is freely available. You can download and use it for the applications into atmospheric studies. Then on board the INSET 3D sounder, there is one instrument for the infra. It has 19 channels, 18 in the infrared and 1 in the visible channel, which is used to study the vertical profile of atmospheric temperature, water vapor, and ozone. So here also it's a kind of an hyperspectral sensor. So we have a low long wave infrared channel where we have 7 bands, middle middle wavelength infrared channels where we have 5 bands, and in the shortwave infrared and the visible channels again we have 8 bands around here. So total of 19 channels are available from the geostationary platform. So this is one of the uniqueness of it, that we use this data is utilized for studying the atmospheric parameters. Then the prime application of the hyperspectral data sets, if you look at it, so we compare it with the existing multispectral capability. If you look into mining and geology, what does the existing multispectral satellite offer? It offers the simple land use land cover classification, whereas hyperspectral, from using hyperspectral data sets, we can go for mineral mapping. So overlooking the drawbacks of the hyperspectral, that large volume, noise, and you need to do a lot of corrections before you can use that data, but it has a significant advantage that this helps you in mineral map, creating a mineral map, identification of different types of minerals on the Earth's surface. In case of forestry, again, existing would help you in just doing a simple land use land cover classification, whereas hyperspectral remote sensing data would lead into identification of different species of forest type. This will give you a general category of forest, but here species of forest would be identified. The identification of vegetation stress, if there is a nutrient stress, water stress, what kind of stress is there? It's a healthy, diseased, what is the cause of those disease factors can be identified. Detailed stand mapping, foliar chemistry, etc. All these applications can be studied using a hyperspectral data sets. In case of agriculture here would help you again simple land use land cover classification, helping you identify different types of crops, maybe due to, we can say, the irrigated, non-irrigated, or to some extent the different types of crop mapping, but limited to a certain extent. Whereas with hyperspectral, we can go up to the soil mapping type of the stress, the deficiency in the soil due to the salinity present in the soil moisture, the crop differentiation, and the crop stress. And in environmental management, it's a land use land cover monitoring can be attempted with the broadband remote sensing, whereas with hyperspectral, one can study the chemical mineral mapping and their analysis. So the main areas of application of hyperspectral, if we say, in geology, it's mineral mapping. In case of the agriculture and soils, we can have for crop production, crop identification, the crop phenology, physiology, and biophysical properties, the crop stress, the biofuel, crop residues. Soils, the high resolution offers the high sampling resolution addresses key issues of the soil chemistry and its genetic and fertility classification. In terms of vegetation, the forest health, canopy moisture stress, then the tree species, the species diversity, photosynthetic activity, plant productivity, the canopy biochemistry, biomass plant transpiration, the crop growth models. All these can be analyzed, studied using an hyperspectral data set. So it has a wide range of applications. In urban applications, we can go for identification of the different materials of the urban surfaces. In case of the buildings, the roads, so what is their constituents can be studied. So this is an example of different types of parking areas with different cemented, coal tar, and concrete surfaces. So each of them can be differentiated and mapped using an hyperspectral data set. In terms of atmosphere, we can study the water vapor, cloud properties, aerosol, absorbing gases, then environmental monitoring, climatology. All these aspects can be studied. The various atmospheric parameters can be extracted with the hyperspectral, specifically the infrared sounder data sets, which I just mentioned. There was a satellite, AIRS, which can be utilized to study some of the atmospheric parameters. For coastal areas and for the oceanographic infrared, you can have hyperspectral data sets can be utilized to study the chlorophyll, phytoplankton, dissolved organics, sediments, detection of yellow substance, suspended matter. So this is another advantages of hyperspectral is, I mean, a synergy of hyperspectral, multispectral, and the microwave data sets. So we just made a simple experiment here where we compared the different spectral resolution data sets and their effect of mapping. What is the impact of mapping on them? What accuracies? So this is a Landsat. This is the EO ALI data, Advanced Land Imager data, and this is a hyperspectral data. So when we classified this, all three data for the same number, the land use land cover classification, the accuracy of the classification was highly improved with the hyperspectral data sets. This is an example where we combine the hyperspectral and the microwave data together to get a better classification, because microwave offers texture, hyperspectral offers a larger dimension, better categorization of objects. So combination of the two, it improved our classification in many of the not all land cover classes, but some of the land cover classes which was difficult with the even hyperspectral because of their smaller dimensions came out significantly improved with the combination of hyperspectral and microwave. So a synergy of this can also be utilized for improved classification of the data sets. Now, significantly important aspects in the hyperspectral data processing is the acquisition or creation of a spectral library. Now, spectral library are collections of spectra of different surface material which is collected either from laboratory experiments or ground-based measurements, because these are our reference which is used to compare with the image collected spectra and then identify different features on ground. So we should have a good collection of spectral spectra of different surface material. And what does a spectral library contain? They contain spectra of individual species, often grouped by the surface types, vegetation versus soil versus man-made, and sometimes they are clubbed by the grain size fraction. And these are acquired at a test sites which represents variety of features, varied terrain and climatic zones. And this database enables identification of materials by matching this reference spectra collected from ground or lab with the spectra obtained from the satellite. Some of the spectral libraries are publicly available, like they are included in the software, or even if you browse on the website, there is a spectral library called as Aster Spectral Library. The spectral library by the USGS is there, from the JPL is there. So there are various spectral libraries which are available publicly. You can utilize those, but they have been created from their own countries, from their own atmospheric and ground conditions, which to some of the features they may match, but not to all, which is dynamic features like vegetation where there is a constant change. You may need to collect and create your own spectral libraries. So it's always advisable that it is better you collect using ground instrumentation your own spectral libraries. In case of the absence of such, you can use the publicly available spectra to compare with the image spectra and identify different features. So in terms of processing, if I look at what we need to do is we need to calibrate our data, do atmospheric correction, create spectral libraries, and then go for information extraction. So here what is there? We have the grasslands. This is the IMS high-C data, which needs to be calibrated. This is my original data. After calibration, after doing atmospheric correction, I need to properly, then I get the proper spectra which will match with my ground spectra, and then I can go for information extraction. So this is an example of the original hyperspectral sensor data before calibration and correction. This is after doing the atmospheric correction. Now it matches to vegetation spectra, which can then be further processed accordingly for extraction of the land use land cover map or the species type identification map or any analysis which you would like to do it on it. And as I said, the same algorithms like the maximum likelihood classifier or minimum distance classifier, which you have studied with the image processing approaches, may not work with hyperspectral data, because even the maximum likelihood classifier is biased by the number of training samples. So it requires a certain number of training samples is necessary if you want to get a group classification with these kind of classifiers. But as the number of bands increases, because they are dependent, the number of training samples required is either 25N or 100N. Now here N is the number of bands. So if I increase the number of bands, then the sampling requirements would be high. I need more ground pixels, more ground data sets, which would be difficult to get in terms of the hyperspectral data. So what we do is, these classifications, they do not perform with the hyperspectral. We need additional or different kind of mapping approaches to go about with hyperspectral data sets. So the spectral matching, there are four categories of mapping techniques. One is the spectral matching approaches. Will not go in detail, but I'll just mention as an overview. Spectral matching approaches like a spectral angle mapper, cross-correlogram spectral matcher methods. Spectral feature analysis wavetrace is by spectral feature fitting, that is comparing the ground spectra with the image spectra. Waveform characterization, and since we have mixed pixels, and within a mixed pixel you have very different land use classes, we have spectral unmixing techniques, which is utilized for categorizing or finding the proportions of different land use land cover present in the pixel. And finally you go for validation. So the main approaches for the hyperspectral data set is first calibration, atmospheric correction, and then creation of a spectral library, and then go for mapping techniques for information extraction. This is an example of the maps being generated for this area using the hyperspectral Hyperion data sets. So you will find that the level of details which you are able to see, that is the hyperspectral sensors, you get much more detailed classification. We are able to identify different species which is present in the area, like sal, teak, pinus. So different species are easily identified.